I want to do a deep dive on graphing a function. The function I want to use has the following formula. F of x is equal to the cube root, rather the 1/3 power of the expression 3x squared minus x cubed. And I've picked this function because it's a little bit more complicated than the ones we've seen in lectures and homework so far. To really get an accurate picture of this graph, I do need to take into account what the concavity of this function will look like. So as I go, I'm going to be keeping track of these features by plotting them out on Desmos. So it's a fair question to ask, why do we learn how to sketch graphs in an era where graphing calculators and computers themselves are ubiquitous? Well, the reason for that is that graphing calculators are a tool and computers are a tool. And we need to know how to use our tools well, or else we might as well not be using the tool to begin with. How many times have you tried to graph a function on a graphing calculator or on a computer, and the picture you look at is blank? Remember that a graphing calculator can only show us a certain window of the XY plane. It's our job to point the graphing calculator to which part of the graph is interesting to look at. So we can think about these skills that we're building up as, what skills do we need to identify the most interesting parts of that graph? So as I start out here, I have a 3-stage process where first I look at all the information I can get out of the formula for the function itself. Then I look at all the information I can get out of the first derivative of the function. And finally, I look for all the information I can get out of the second derivative of the function. So with the formula of the function, I'm going to ask myself, where is this equal to 0? And are there any x coordinates for which the formula is undefined? As I go, it will be more helpful to rewrite this formula in a couple different ways. So I can also think of this as taking the cube root of a polynomial. That polynomial is x squared times 3 minus x. So that's going to be a little bit more difficult when it comes time to differentiate. I probably won't use this when I differentiate, but it helps me to see that this formula will equal 0 at 2 different x coordinates. So at x equals 0 and at x equals 3. Both of those values will give me 0, which I then raise to the 1/3 power. 0 to the 1/3 is still 0. Now, are there any values for which this formula is undefined? No. Every real number can be cubed. 0 cubed is 0. The cube of a positive number is positive. The cube of a negative number is negative. So all real numbers also have cube roots. I do not need to worry about the cube root function being undefined anywhere on the real number line. Okay, so are there any asymptotes of this function? Well, I'm not expecting any vertical asymptotes because my function doesn't have any places where it's undefined. A vertical asymptote by definition would be somewhere that the formula is tending towards positive infinity or negative infinity. Now, does this have any slant asymptotes or horizontal asymptotes? That's a more interesting question. Now, when I look at this, I can see I've got, let's rewrite this one more time, negative x cubed plus 3x squared, all raised to the 1/3 power. So as x becomes larger, it's tempting to think that this x cubed will be the only part of the formula that matters, and it will dwarf x squared by so much, we may as well not have that x squared. That's a pretty heuristic argument. In order to shape it up and make it a little bit, accurate, useful, let me go ahead and rewrite the formula like so. So I am always allowed to rewrite my formula by multiplying by a value of 1. Here, I will say this is negative x divided by negative x. And the reason that I've done it this way is because I'm trying to set up this slant asymptote idea. So I can keep my negative x on the outside there, and I will bring this 1 over negative x inside the cube root, where I will have to write it as negative x cubed. Now, as x tends to infinity, this stuff inside the cube root will start to look like 1 plus 3 divided by negative x. Or how about minus 3 divided by x? That'll be a little bit easier to look at. And then outside here, I've got my negative x, like so. So maybe I do have one of these slant asymptotes at negative x, with a slope of negative 1. Let's go ahead and plot that. So I'm expecting slope of negative 1. I also said that I've got a 0 of this function at exactly x equals 0 and x equals positive 3. Okay. So these two vertical lines are indicating where I'm expecting to find zeros of this function, and this blue line is where I'm expecting to find a slant asymptote. Let's go back to the whiteboard. The next thing that I want to do is calculate the derivative of this function, and that will be most convenient to do using my original formula. The power rule says bring down the 1/3. The chain rule says the inside of the function stays the same. Multiply by the derivative of the inside. And what did I forget here? My new exponent needs to be 1 less than my old exponent. Once again, this will be more useful to write in a slightly different form. Let me put the 1/3 on the outside. Let's say I've got a denominator of 3x squared minus x cubed. This is all raised to the 2/3 power. And I have a numerator of 6x minus 3x squared. And once again, if I really wanted to, I can factor that denominator. So what do I have raised to the 2/3 power? I already know from my earlier work, I've got x squared times the quantity 3 minus x, all of that to the 2/3 power. And again, numerator of 6x. Let's go ahead and call this 3 times x times the quantity 2 minus x. Okay. So what are my critical values? Critical values are the only places where this derivative can change from positive to negative, right? Those are the places where either the first derivative is equal to 0 or the first derivative is undefined. So this formula is undefined for x equals 0. I'll be dividing by 0, that's not allowed. And x equals 3. Okay. Is this equal to 0 anywhere? Well, I could try x equals 0, except, like I said, the formula is undefined there. But f prime of x will be equal to 0 when x equals 2. That's definitely a true statement. Now, is the function going to be increasing or decreasing there, right? So for x equals 2, this numerator is going to be 0, and this denominator is going to be positive. For values of x larger than 2, I'm expecting this derivative to be negative. Again, because of the squaring here in the denominator, that's always going to be positive. For x greater than 2, 3 times x will be positive, but 2 minus x will be negative. And likewise, for values of x smaller than 2, I'm expecting this derivative to be positive. So what kind of point am I expecting here? I'm expecting, right, it increases and then it decreases. This should be a maximum of the function. Now, these other 2 points here, 0 and 3, I already have those marked on my graph. So x equals 2 is where I'm expecting to see something interesting. I'm expecting to see a maximum here. What about for the other 2 coordinates, for x equals 0 and x equals 3? Well, if x is a number larger than 3, then 3 minus x is going to be negative. All these other things are going to be positive. So then my derivative would be negative. What happens when I have a derivative that is increasing and then, excuse me. So my x is greater than 3. 3 minus x will be negative, but so will 2 minus x. Sorry about that. So I'll have something that is decreasing and then increasing. I'm expecting to find a maximum there. And the same thing if x is a negative number, if x is less than 0, then my derivative, this will be negative times negative divided by negative times negative times negative, right? Negative and then positive. So I'm expecting, let's say, minimums, local minimums at x equals 0 and x equals 3, and a maximum, a local maximum, at x equals positive 2. So I have all of those marked on my graph. The last thing to do here is to check concavity. So my second derivative, it'll probably be easiest to think of this as a quotient rule. So my numerator and my denominator are going to just be coming from the quotient rule here. Let's say this is 1/3. Denominator is 3x squared minus x cubed, all to the 4/3 power. Numerator, I'll have the old denominator, all that stuff to the 2/3 power, times the derivative of the old numerator, which here is going to be 6 minus 6x. And then I subtract off 6x minus 3x squared, all times the derivative of that old denominator. So 2/3 x squared, 3 minus x, all of that to the 2/3 minus 1, so negative 1/3 power, then times the derivative of what's inside. So let's call that 6x minus 3x squared. And this set of parentheses I did not fill before, that was 3x squared minus x cubed. Okay, well, that's a little bit hairy, but you know, it's just going to be tedious to work with. It's not so impossible that I don't know what to do. Now, this will be much easier if it were polynomials. So I'm going to multiply on the numerator and the denominator by 3x squared minus x cubed, the 1/3 power. Right? I can always multiply by 1, just a slightly different way to do it. So my numerator will now be 3x squared minus x cubed to the 5/3 power. And my numerator is just going to be a polynomial. Taking something to the 2/3 power and then multiplying it by itself to the 1/3 power, I'm just going to get 3x squared minus x cubed times 6 minus 6x. And I will subtract off 6x minus 6x squared. And then having something, times 2/3. And then having something to the negative 1/3 power and multiplying it by itself to the positive 1/3 power is just going to be 1. So here is a slightly more useful formula for this second derivative. Let me move it up here. And I can also go through and multiply this out. So what am I going to have left over after the dust settles? That numerator, it turns out, is just going to be 2x squared. And that denominator is going to be my stuff all to the 5/3 power. So that can be something you can work out. I'm a little short on time at the moment. So where can this be 0 and where can this be undefined? Well, 0 is one possibility, and so is x equals 3. So is this second derivative positive or negative in between 0 and 3? I'll just plug in, say, x equals 1. I'll get a numerator of 2, a denominator of 3 minus 1 to a power. That'll be a positive second derivative. And then for x larger than 3, the second derivative will be negative. And for x less than 0, the second derivative will be negative, right? That numerator is always positive. And then down here, if I put in x equals a negative number, I'll get something negative. Now, let's put all of this on the graph and see how well we did. Where did it go? Here it is. So I'm expecting this function to change concavity at 0 and at 3. So let's polish this up a little bit. What am I expecting this function to look like? It should be, remember, it should be concave up in some of these places, and it should be concave down in other places. So concave up between 0 and 3, concave down to the right of 3, concave down to the left of 0. So my generic picture would look a little bit like this. So concave up here, concave down here, concave down here. Now let's actually check this against the graph itself. Remember, I'm expecting minimums and I'm expecting a maximum. So let's turn on this graph and see what we got. A minimum here at x equals 0, a maximum here at x equals 2, and I dragged the picture, but the thing doesn't change. Well, what happened here? I've got a vertical tangent line, so that is one of my critical values. The function is decreasing to the left and then decreasing to the right, so that wasn't a minimum at all. I can get rid of that. If I zoom out, I have control over this graph. If I zoom out, I can see that I do have this slant asymptote for x equals, with slope -1 and y-intercept 0. So all of these interesting features of this graph I got by calculating its derivatives.